Another obvious extension of a Turing machine is to have multiple tapes, each with its own tape head. But as with Turing machines with doubly infinite tapes, we can regard a multi-tape Turing machine as a single-tape Turing machine, where the tape head can be on any of a number of sides of a tape. Now, since the tape heads might move independently, the moves should also be considered. So, in general, the moves will be of the form our Turing machine is in state Q, and the symbols at the different tape heads are alpha, beta, gamma, and so on, and we're going to move to a new state Q prime and change those symbols in some fashion, and the tape heads will then move in some fashion, where the tape symbols and the tape head positions may change. And so the multi-tape Turing machine doesn't really introduce any new capabilities. We could also have non-deterministic Turing machines. But as with pushdown automata and finite automata, any non-deterministic Turing machine can be rewritten as a deterministic Turing machine, so even including non-determinism doesn't extend the abilities of our Turing machines. However, we can, as with the pushdown automata and the finite automata, we can use the multi-tape and non-determinism to make it easier to describe a Turing machine for a language. So again, let's consider our language of equal numbers of A's, followed by B's, followed by C's. We were, with some effort, able to write a Turing machine for this language. But we can write a much simpler multi-tape Turing machine. And to do that, we'll use 4 tapes. One for the input string, one that will record the number of A's, one that will record the number of B's, and one that will record the number of C's. And so our metacode will copy the A's onto the first tape, will copy the B's onto the second tape, crashing if there are any A's among the B's, and then copy the C's onto the third tape, and again crashing if there are any B's or A's among the C's. And then we'll remove an A, B, and C from each tape. And if at any point it becomes impossible to remove a set, crash and reject. Otherwise, if all 3 tapes are emptied, accept. And another useful extension of this Turing machine, which only produces another Turing machine but makes it easier for us to work with them, is the idea of chaining 2 or more together. The process is the same as chaining 2 pushdown automata or 2 finite automata. If one Turing machine reaches a halt state, we'll define that halt state to be the initial state of a second Turing machine. This allows us to design Turing machines component by component. For example, we might construct a Turing machine that will put an X at the end of a string, and we'll assume that our language alphabet just consists of the symbols 0 and 1. The obvious strategy is to have the Turing machine move right until it encounters a blank space, so our initial blank space will change to state Q1, reprint the blank, and move right. And then, from there, if we encounter a 0 or a 1, we'll reprint it and move right. But if we encounter a blank space, we'll change state to QL, print the X, and move left, where our state QL prepares us to move back to the beginning. But will this work? So remember, mathematicians care about existence, computer scientists care about algorithms. While the tape for a Turing machine contains a finite number of symbols, these could be separated by any number of blank spaces. So how can we verify that there are no more symbols after a blank space? Mathematically, we know there is a last symbol, but we have no way to find it. Or can we?